Hello. It is exactly the wrong time of day for me to be doing this. It's if you look in the left-hand corner, it's 11 p.m. But we have two more problems to go through. When this exam was posted for Park section, I downloaded the earlier copy that didn't have the last two problems. So we are going to go through these now pretty quickly. So let L be a linear transformation from 2 dimensions to 3 dimensions, such that L when we plug in 1, 2 gives us this guy, and L when we plug in 3, 2 gives us that guy right there. And we are told to find L at -1, 2. So we know that one of the properties of a linear transformation is that it works under vector addition. And what do I mean by that? Well, a x1 plus a x2 is equal to a x1 plus x2. We know that this is true. We also know that r a x is equal to a rx. So we can use these two facts to solve this system of equations that we're going to make here. We can take this column vector, 1, 2, and put it together with this column vector, 3, 2, and we are going to set up an augmented matrix to find the linear combination of these two vectors, which gives us this vector here, -1, 2. And we already know that this vector is in the span of our first two, and we know that because these two guys are in 2 dimensions. They're two-dimensional vectors, and they're not multiples of each other. So if we were to graph these out, we would have 1, 2, and let's see, 3, 2, 3, 2. Whoops, can't do that. 3, 2, and they're not on the same line. So they are going to span all of two-dimensional space when we take our linear combinations. But we have to figure out for what values of x1 and x2 gives us -1, 2. So let's solve for that. We are going to subtract two row 1s from row 2. We will get 1, 3, -1 is 0, -4, and let's see, 2 is 4. And then we can simplify this down and subtract here. Subtracting 3, adding 3, 2. So there we go. We've solved our system. We see that x1 is equal to 2 and x2 is equal to -1. And we can, I'm going to move down here, we can translate that into 2 times 1, 2 plus -1 times 3, 2. And when we solve this, you'll see that we, in fact, do get -1, 2, which is our answer. But since we know that the transformations that each one of these goes under, they all undergo the same transformation L, since we know our two properties that L works under vector addition and scalar multiplication, we can just apply these values, 2 and -1, to the output vectors. So we'll take 2 times 0, 1, 4, and we will add -1 times -2, 0, 1, and out will pop 2, 2, 7, which is our correct answer choice. And I'll just stick this, I guess up there. Okay. Question 16, let A be an m by n matrix. Which of the following statements is always true? So I do not have the proof for this fact memorized. I'm sure you can look it up on your own. There are a bunch of proofs for this. I don't have any of them internalized. So we know for a fact that the rank of A is the same as the rank of A transpose. That doesn't matter. It doesn't matter what dimensions you're in. M could be 100, N could be 3, and this will still hold. And what you can translate this to mean is that the number of linearly independent rows is the same as the number of linearly independent columns. So we know that this is our answer choice. We also know that, let's see, that the number of columns is equal to the rank of a matrix plus the nullity of a matrix. And you can also make this a little more formal and say the dimension of the column space of A, just like you can translate this to say the dimension of the null space of A, like that. And so from this fact, you can go and prove that all of these other ones really are false. Let's see, mainly, sorry, if we take a look at A, the nullity of A is the same as the nullity of A transpose. Well, if M and N are not equal, we're going to have a different number of columns when we transpose our matrix, but we know that we'll keep the same rank. So nullity, the dimension of the null space will have to change in order to compensate for that. The same applies for C, except for different reasons. So the column space of A is the same as the null space of A transpose, and this is sorry, right now at 11 p.m. I don't really have a good explanation for this. I'm sure if you use this as a Google search term, you will get something out of it. And I'm sorry, that's it's not often, but I admit defeat on that one. I'm not exactly sure, not right now. But D and E, we do have some good explanations for. So the columns of A form a basis of the column space of A. So you might think that that seems pretty good. That seems pretty true. That the span of A1, A2, A3, all the way to AN. It seems like a true statement that these guys are the basic building blocks that you need to build out your space, this span here. But it can be the case where we have some of these columns that are redundant. So if we're dealing with, say, a 3 by 2 matrix and we have 1, 0, 0, 1, 2, 3, we can take a look at this and see that the column space, in the column space here, this vector on the end here, 2, 3, is completely redundant because with our first two vectors, we are going to have two linearly independent vectors. So we're already going to span all of our 2, and so that second one, our third vector here is not included in the basis because it doesn't actually add anything to our span. And similarly, and I think even more incorrectly, the columns of A transpose do not have to form a basis for the null space of A. Probably for other reasons, but definitely for the reason that we laid out here, that there can be columns or rows when we transpose that don't actually contribute anything else to that vector space. Okay, hopefully this was helpful. I'm a little annoyed that now these two questions aren't connected with the main video, but I hope people found that a little bit useful.